In this quick demo, we will be using the latest version of Nostrum web app to reproduce some of the computational results published in this Nature Catalysis article. Our goal is to predict the relative activity of different compounds with our computational methods and find certain correlations with experimental data reported in this study. For this purpose, we will be using the protocol offered for free on our corporate website. And as you will see, even with this simple approach, we will be capable of determining which compounds are more susceptible to be degraded by these artificially designed ester hydrolases. We will start taking the structure of a double mutant of Fragaceatoxin C. Actually, it's the second one suggested in the article. And we will use the molecular visualizer embedded in the web to identify the catalytic region and check that it looks good. In the paper, we see that this mutant introduces the following changes. First, in position 38, and we can go there if we click here in the sequence, there is this, the aspartic acid that is replaced to a serine. And actually, this is the serine that will perform the catalytic attack. Then, in position 173, the glutamic acid is mutated to glutamine. We see how both mutations are correct, and we can also observe the catalytic triad. We see how serine participates in a hydrogen bond with this histidine, and the histidine at the same time has its epsilon hydrogen interacting with the glutamic acid from above. So everything looks good at this initial stage, and this means that we are good to go to submit our first calculation. The first thing to do is a rigid docking to place our compounds near the catalytic serine. To run the docking, we just need to go to the docking page and supply the initial structure for the receptor. We can upload it from our local files, and we can view it again with the molecular visualizer. Once the structure loads, we can try to locate again the catalytic region. So we select the right chain, the right residue using the sequence. This is the serine that we mentioned. And now we can use it as reference to define the docking cavity. We can manually introduce the 3D coordinates, or we can define them by enabling the select center button and clicking on an atom near the binding site. In this case, we will click the alcohol group of catalytic serine 38. This is the box, we are able to see it, and we will set a slightly bigger cavity, so all our compounds fit in it. And before doing anything else, we will go under the structure settings window, and we will be disabling the fixed topology option, because since we have already checked our initial structure, we don't need it to be fixed. And the only thing that remains now is to define the ligands that we want to dock. In order to define them, we should go up to this place here, and by clicking in this icon, instead of uploading the file containing our ligands, we can define the smile tags for them. So let's do it. So for this demo, we take 4 compounds from the publication. We can take their smile tags and paste them in this field from here. And once we do, on the right, we will be able to see the 2D structures for all of them. Okay, so as you can see here, we have 4 molecules, and all of them have at least one ester group, which is the chemical group that our catalytic serine will attack. Once our ligands are set, we can submit the simulation going to the lower part of the page. There, we will simply pick a name for the simulation, let's call it docking, and then finally, by clicking the submission button, our calculation will be sent to the queue. And if we wait a few seconds, we will be automatically redirected to the dashboard. If the queue is not full, we'll see how our job starts. Once it does, we should get our results 15 minutes later. Now that our job has already finished, we can click on this eye icon from here to access the results view. There, we can check the dock poses obtained for each molecule. Once everything is loaded, we first will see this plot where the different results for each compound are shown. Here in the y-axis is the docking score, for instance. And if we go down a bit, we will see the table containing the best pose for each ligand. We also have this molecular visualizer that we can use to display the different poses that the docking produced. Now we are changing its representation in order to see all the atoms of our system, and we are also activating all the poses so all of them are displayed in the visualizer. And here the goal is to see how all of them are near the catalytic setting that we first identified. And after this quick test, we are ready to simply take the poses with the best score, those summarized in this table, and start an induced field refinement simulation with Pele to optimize them considering the flexibility of both the small molecule and the protein. We can do so by clicking on this button. When we click, we will access the submission page for the IFR. Here, there are a few parameters to set up for this specific example. First, we should disable again the fixed topology option to rely on the original structure. We will then choose the OpenFF force field and will increase the amount of sampling to ensure we will have enough. We finally must ask Pele to track a few distances belonging to the catalytic triad, as we will need them to determine the catalytic activity of each compound. To add them, we go to the Simulation Distance tab and ask for a new distance. We start by defining the distance between the ester group and settings oxygen. We can manually write the atom selections or enable the selection on the molecular visualizer, as we will see. In this last case, we can simply click on the corresponding atoms. The first atom, in this case, is the carbon atom of the ester group of our ligand, and the second one is the oxygen atom of the alcohol group of our catalytic setting. And now we are ready to add the second distance, which is going to be between setting and the histidine that is next to it. So we first must select setting's hydrogen, and then we will do the same with histidine's delta nitrogen, which is here. And lastly, we will add the distance between histidine's epsilon hydrogen and the carboxylic acid group of glutamic acid. In this case, there are two potential oxygen atoms that may interact with histidine, so we will define both distances. We select the hydrogen from the histidine and then the oxygen atom that is looking down. And we will repeat the same process, but selecting this time the oxygen atom of glutamic acid that is looking up, that is here. So now we have the four distances defined and everything is ready for submission. We will apply the same settings to the four compounds, and in the case of glyceryl 3-propionate, since there are three ester groups, all of them will be considered by including the distance between setting and each of them separately. And now we are only missing a name for our job. Let's call it refinement, and then we can go ahead and submit the simulation. We then again will be automatically redirected to the dashboard, and here we will see the simulation that we have just submitted. Now, as we said, we will have to repeat the same process to launch an induced field refinement with the rest of the compounds, and eventually we will end up having 4 simulations submitted to the queue. After 20-30 minutes, all simulations will finish. We will need to download the results to run the analysis script published with the manuscript. To download them, we can click the cloud icon. We can also check the results on the web by clicking the eye. In the results view, it is interesting to check the energetic profile where all structures sampled with Pele are shown. We can select the metrics to display. In this case, we are interested in the catalytic distances that have been previously defined. We have them here. Catalytic activity is predicted in the original paper, measuring the amount of structures where distances required by the catalytic event are below 4.5 angstroms. We can see in the plot how there are a bunch of structures satisfying them. If we click one of these structures, we will incorporate that structure as a row in the table below. So this is the structure that we click, and we can see how all the distances, the catalytic distances, those that are meaningful for the catalytic event, are below 4.5 angstroms. The number of structures that fulfill these conditions is what is used in the paper to quantify catalytic activity. This calculation can be done with a script published along with a manuscript and is available in this link. The values from this calculation are then correlated with the experimental activities, and we can obtain a great correlation, similar to the one that was published. This figure shows the final correlation that we got using the protocols from the web app. We can find experimental activities in the horizontal axis and predicted activities in the vertical axis. So, to conclude this demo, we can highlight how these quick and free protocols offered in Nostrum's web app can be very helpful and give powerful results that can help elucidating catalytic activities in today's example, but also many more things like admit properties, binding modes, or binding affinities. We hope you liked it, and we invite you to give it a try.